Welcome to the CSound Generator. To get the program, go to the GitHub link in the description below. Grab the archive file, download it, and uncompress it. When you have done this, you will see the following files. The top-level directory includes the user guide, which explains everything I will cover in this demo, and then some. The CSound Generator is actually two programs. The generator itself creates CSound score files. The Scale Notes Generator creates scales and chords for all possible combinations of scales in microtonal tunings. The rest of the files in the top-level directory are informational. The source directory includes both C and Python code. The test generator directory contains sample config files for the generator itself. And the test scale notes directory contains sample config files for the Scale Notes Generator program. So let's create a score file. The first file needed is the notes file. This is where note names are assigned and cross-referenced with frequencies. Note names are made of the octave, which is 0 through 9, a note name, which is an upper or lowercase letter, and a modifier, which is a blank, a number, or either case letter. This file is for a 12-tone tuning. And this file is for a 15-tone tuning. Each file allows 10 octaves, 0 through 9. This is pretty much covering the hearing range. You can see that I added the notes H, H sharp, and I. This file defines sound samples for percussion or sound effects. The frequency is a multiplier that allows the sample's frequency to be as low as a quarter of the original. This increases in tenths to equal the original, or continues to be as high as 5 times the original. You can split this up however you want to. I chose tenths. This can produce an impressive array of toms ascending or descending. The next type of config file is the Staves file. This is where the music is made. Each staff is defined with an instrument. The first instrument here is a simple sine wave. This is followed by a series of notes. The notes are defined with a keyword, in this case fund for fundamental. Then the note from a notes file. And then the start time, the duration, and the volume. In the example, the second instrument has sine wave harmonics for comparison. It starts at 6 seconds and plays the same melody. Next, another instrument is added. It plays a counterpoint to the sine wave instrument. And then a third instrument is added, and so forth. This is to demonstrate some of the range of instrumentation, as well as how to define them. When the percussion and bass are added, the example is repeated once. Since the melody is 6 seconds, the repeat period is 6 seconds for each staff. Notice that the percussion uses notes from the Sound Notes file. After this plays, examples of other types of instruments are played. These demonstrate frequency modulation, amplitude modulation, wave shaping with a single oscillator, and wave shaping with 2 oscillators. Finally, there is an example of vocal sounds using the CSound FM voice opcode. Notice that the keyword is VFund, and there is a vowel at the end of the definition. The next config file is the template file where instruments are defined. First, waveforms are defined. Sine waves are built into CSound, and that is the first definition. CSound allows for custom waveforms. An example of those are provided here. Jagged sawtooth, W, and the combo saw and square waves are examples of what can be done. The last squiggly wave is used for wave shaping. But the interesting part of this file is in the instrument definitions. The start value is added to the staff fundamental start, while the duration is multiplied times the fundamental duration. The volume is relative to 1,000, so in this case 0.8 is multiplied times the fundamental volume. The frequency is multiplied times the fundamental note frequency, and next is the waveform, which is the sine wave here. The last 4 fields are the ADSR values. The sine harmonics are the octave, the fifth, the second octave, and the fourth. And notice that the volumes decrease by half for each one. Also, the ADSR is somewhat different for each harmonic, giving the instrument texture, especially with high notes, which can be harsh otherwise. The scale harm keyword introduces a special case for microtonal music. The frequency value is used as an index into the list of notes. It is added to the fundamentals index, and it is correctly 0 for the first note in the package. And the corresponding note frequencies are used as harmonics. Beat harmonics are simply notes that are slightly detuned from integer multiples of the fundamental to create a richer sound. The brass instrument is an example of how complex real-world instruments are. In my paper, An Analysis of 15 EDO Microtonal Scales, I discuss this more completely and provide references to an in-depth analysis of real-world instruments. The link to this is in the description below. The brass instruments uses the sawtooth waveform for a bright sound, but includes low-frequency notes to simulate a player's breath. These die away quickly, which adds a punch to the beginning of the note, but doesn't interact with the note. The fixed keyword means that the frequency is always the assigned value. And in this case, they also die away quickly. The xylophone is just a metal bar. The physics of metal bars are complicated, but it's possible to find tables of harmonic frequencies that can be used to generate various bell sounds. Hammered string instruments are also very complicated. The strings have rich harmonics for which the volume is 1 over the number multiplied to get the frequency. But there is also the bridge and other strings that affect the timbre. And the act of striking strings is similar to striking a drum, except that it dies away quickly. And there are other factors as well that I haven't accounted for. But I'm not trying to reproduce real-world instruments, just interesting ones. That is why there is a left and right channel for this. It allows for panning, but also interesting effects that I cover in the instruments demo. The plucked strings instrument is similar to the hammered strings, but the harmonics are not as rich, and the volumes are 1 over 2 times the frequency multiple. The woodwind instrument has harmonics that are even multiples of the fundamental. The detuning is to make it sound less flat. This also has breath sounds. The bowed instrument has rich fundamentals and a little bit of the resonance from the body. But with some understanding of real-world instruments, it is time to start inventing your own. Here, a low-frequency note is used to shape the overall sound. But the harmonics are a mixture of triangle, sawtooth, and sine waves that fade in and out as the note is played. It takes some experimentation to find settings that sound musical, but I find it to be well worth the time and have spent quite a few hours discovering how to create them. The mild wave mixtures are another variation on this method of creating an instrument. It uses the start time and duration and the ADSR to change the harmonics as a note is played. Notice that the later harmonics are quieter than the earlier ones. CSound also supports more traditional synthesizer techniques such as frequency modulation, with a fair amount of control over its parameters. And there is amplitude modulation with similar levels of control. Wave shaping is somewhat like using the low-frequency additive method, but it uses modulation as opposed to simple blending. And wave shaping with 2 oscillators creates distinctly electronic effects, especially with custom waveforms. Next, there are the sound samples. These can be used for percussion or sound effects like thunder. And finally, CSound can create voice formant waves for vowel sounds. These require the vowel definitions that set the FM voice ID to a name. The template file instrument definitions correspond directly to instruments defined in a CSound orchestra file. I took examples from the CSound book and modified them. I highly recommend that book, and there is a link to it in the description. This is the most basic definition. The parameters from a score file are positional, which means that CSound identifies them according to the order they are found in the score line. They are then applied to the instrument definition as appropriate. Each instrument must have a unique definition in the orchestra file. This means the non-positional variables must have unique names. Now these are the hammered string definitions, and creating the right and left channels is as easy as setting the opposite channel to 1/10 of the primary. The frequency modulator uses the CSound opcode that is specifically built for this. It has several parameters to control the level and speed of the oscillation. The amplitude modulator is somewhat simpler and simply runs the volume through an oscillator. The single oscillator wave shaping is handled similarly to amplitude modulation. The original wave is run through an oscillator using a separate waveform. The double oscillator wave shaping is based on the same principle but is somewhat more complicated. The effects that it produces are fascinating, and I am continuing to find new ones. Sound samples are read and can be modified by pitch, hence the multiplier in the Sounds Notes file. But they are basically played as is. The samples in this demo are included in the package. Again, the FM voice opcode generates vowel sounds. Now it is time to generate a score file and create some music. As I said, the sound samples are included in the test directory. To use the C program, it must be compiled, which means that you must have a C development environment installed. To use the Python application, simply install Python 2 or Python 3. The application supports both. The package includes a script file to run the test. It uses the Python 2 application. The two notes files are defined, but basically defaults are used for everything else. After the score file is created, it is used by CSound to produce a wave audio file. Here is the score file that CSound Generator creates. The first instrument is the simple sine. Let's listen to the audio while looking at the rest of the file. The second application in the package is the Scale Notes Generator. There is a script file to run this test as well. It's using the C version of the application. The command line is a bit more complicated. Both the scale and notes files should be defined because there will be more than one of these as you analyze scales. The other parameters are described in detail in the Scales Notes demo. Since there are many files that will be produced, they will be stored in the Scales directory. The script reads the Staves files created and runs the generator on each one to create a score file. It then runs CSound on each of these to create a wave audio file. The files are named using the steps between each note and the generated scale. These can then be compared. Again, the Scales Notes demo goes into detail on how to use the application and also how to use the output for composition and analysis. The remainder of this demo covers administrative tasks. To install the application to your system, you must be super user. I have to confess that I found a few bugs while making these videos, but they are fixed in the package. An example of this is that the Python versions are installed along with the C versions. I have attempted to provide enough documentation to answer most questions. This includes man pages for the Unix-based systems. And if you need to uninstall the application, this can be handled by superuser running the make file. Finally, if you are a coder and want to work on the C application, the make command should work as you expect. I hope that this application will be useful to composers, anyone studying the harmonic structure of instruments, and those who are interested in adding to the theory of microtonal scales and chords.